Okay, so yeah, first of all, thanks for the warm welcome. As Oliver mentioned, so we worked together roughly 4 years ago for some time at Intel. Since 3 years, I'm mainly based in Finland, but still living in Munich. So for me, this conference was quite easy and simple to come here. I basically traveled here by bike. Probably had a much shorter way than most of you. But then maybe let's just start from my side. So challenges in verification of SOCs for 5G and beyond. And what is not mentioned here, it's really for infrastructure 5G. It's not about the modem. So it's even about bigger chips. So I got inputs from a lot of colleagues at Nokia and also outside. So I mentioned here some of the names. Some of the people who contributed are even here at the conference. And maybe let me just start with, hopefully this is now working. Yes, it's working. So just this is the outline of my presentation. So just to give a little bit of introduction on where we are coming from, then talking about what is Nokia doing on 5G infrastructure, because the typical reaction what you're getting today at Nokia still around, you stopped doing handy, so what are you doing up to date? So we are still 100,000 people and more, mainly working in mobile infrastructure, and a big important part of this infrastructure as of today are our SOCs. So that's also, there's a lot of semiconductor development happening right now in Nokia. Then a little bit about, so what does it mean, SOCs for 5G infrastructure? What are the characteristics? And they're quite different from a typical modem design, which I know out of my time from at Intel. Then talking a little bit about the verification challenges, which are partly coming out of them, what we have seen, and some of the challenges which are probably also quite common for a lot of you who are working in verification. Then for sure talking about our approaches, for sure not giving all the details, but giving some kind of directions, also including us to some people here in the room, to the ecosystem, and then basically finishing with a conclusion. So let me see how much I will keep my time. So maybe just, first of all, so base station and the radio overview. So this is a typical base station product, and as you can see, it consists. It's a very complex product. It has multiple custom SOCs, and for example, here on the radio side, today one classical product looks like with 16 of our own radio devices on it, DFE devices on it. So, and in the end, our product is measured by this whole stuff has to work together. There are not too many standard interfaces. It's not like, like a typical SOC where you just have to run software on it and there's a bit of communication in between. Really the data path has to come here from the backhaul interface up to the radio. Everything has to work. And this is basically describes also a little bit of our challenges, that on the one side we have to look into get the chips working together with the next chips connected to them, but then for sure in the end we have to get the chip, the product plus software working together in different variations, and maybe let me just even go to the next slide for a couple of different products, because the idea is for sure, because the volume is not so high as in the baseband side, so we have to use the same chips ideally for a lot of different products. Might be again this base station design, it might be some kind of smaller solutions, it might be some kind of standalone outdoor solutions, might be about meshes, MIMO, and also VRAM acceleration. So basically, we need to design our chips for a couple of different applications, a couple of different products. For some of products, we might even not know at the time we are designing our chips. Because, and I will maybe just talk about the next one. And this is a little bit the complexity we are seeing today, and some of them are also quite different from my consumer time. So 200 square millimeter plus, minus in 7 and 5 nanometer. As I said, full products consist of multiple SOCs working together. When I'm talking about verification, typically it's a very long runtime. We have to simulate at least 10 milliseconds of real time in whatever verification tool. We will talk later on about it. We need to ensure inter-chip co-working, so we have to ensure that different chips are working together. Might be even with our own chips, might be with other chips, because not every chip in these products will come from us. We have very long development cycles, and another challenge, and this is even getting more challenges with today's nodes. Lifetime is in the range of 10 plus with up to 15 years. You know, as an example, right now, just got some error message from one of our customers for a product which has been developed 10, 12 years ago, where probably 80% of the team might be no more there or has been moved to completely different locations. And it's on the one side, it's really a support topic, but it's also right now with 3 nanometer, 5 nanometer, it's a silicon reliability topic. So it's somehow we are even closer getting to automotive and these lifetime requirements. But on the other side, we have this push from technology to even smaller nodes. So this is a little bit, this kind of, trying to balance these two topics. Then for sure we have, just the architecture as I described beforehand, because we have to support a lot of different use cases with the same architecture because of the volume, money gain. The architecture is quite complicated. And we have to simulate this complicated architecture, which means some challenges there. Then classical biggest challenges in an infrastructure chip is that, carriers unfortunately want to change the configuration on the fly. Something is happening in the network, they have to change the carrier configuration. And now you can imagine we have huge amount of carrier configuration, and now the dynamic switching between two carrier configuration means you have endless possibilities for dynamic reconfiguration, which means basically it's impossible to verify everything up front. Sounds quite interesting, exciting, challenging. Then on top of this, what we are now getting is also increased focus on energy efficiency, obviously for some good reason, we all know. And for sure also security, there's another reason. And this is suddenly pushing also into the verification domain, because this is now also just starting, because I must admit up to now probably the focus on energy efficiency and real security has been less. So, and this is now for sure also going into 6G, 5G advanced, we will see more and more requirements. Okay. So then from our development cycle, so what are the verification requirements, what we see? Okay, we need fast turnaround regression cycles. Ideally less than a week, so we basically have to conclude our verification in roughly 1 week, and this is indeed quite challenging, going together with the complexity of the chips and the 10 milliseconds and more. Input and output data is classically coming from some kind of modeling. This might be algorithmic modeling which is running in parallel, or we are having gigabytes of data which will be fed into this, into our verification and needs to be compared afterwards. We for sure need a clear view on coverage across all hierarchy, and I will talk about some of these challenges later on. We also have to fulfill very specific use cases, because typically, in order to, so it's not just about random verification, you really need to have very specific use cases, because in order to prepare virtual layer 2, layer 3 call. So this really requires to prepare specific use cases in order to make the bring up for the guys on the top easier. We also we need to simulate real use cases. This means not only use cases which are coming out of MATLAB simulation, but ideally really out of a real world, because the one is this kind of sunny weather verification, but we also have to think about the rainy weather. what is happening when there are mistakes coming in, when we have challenges, when we are, touching the boundaries. Yeah, classical thing, we also have to prepare in our verification environment for silicon validation. So we have to do as much as possible for pre-silicon. And as I mentioned, power and security is getting more focus. Okay. Then maybe now talking more specific about verification challenges on our side. So, yeah, driven by the number, complexity of the chip itself, number of features, then addition high programmability. So we have a big parameter space, no standard interfaces. Sometimes we would love to have standard interfaces. However, then we would have a performance problem. No exhausting testing is possible, period. This is an interesting discussion we're having sometimes with our customer, that in the end, it was impossible to test each and everything upfront, except our customer, and our customer in this case is more our internal customers, which are basically compiling the products. Somebody is now smiling because he knows the situation, coming back to us and saying, it's not working, but why did you not validate? Yeah, you didn't tell us beforehand. And this is a little bit, the kind of challenge we're having today. It also means that gate level simulation, for example, is an interesting case. It really takes forever. Then on top of this, usual challenge, and we have seen this already at Intel, our products are working with software. And are depending on standards, they're depending on inputs. Usual situation for SOC development, all this is coming too late. Specification is changing all the time, all the way along the design. Standards is part of the problem we are doing because we are doing advanced chips. Standards are getting very late, so you will have late changes, you have to accommodate them. And on top of this, in our case, it's also typically software is working on today's products, but have less focus on tomorrow's products. Unfortunately, because we are doing SOCs where software is running on it, the features are sometimes really dependent on the software architecture. So this is additional challenges. Then, as I said already, randomization versus use cases. So there's a lot of push for randomization. Yes, we need this. We need this in order to achieve coverage on all levels. But we also still need to implement specific use cases. And we always need to find the right balance. I already talked shortly about these sunny weather versus rainy weather cases. And sometimes the challenge is how to get these rainy weather cases. How are you getting these kind of challenges, verification cases for technology which is not yet out in the field? You can take some old data and can try to extrapolate it, or you can include some kind of errors, mistakes. So that's a bit of the challenge we're having today. Then distributed verification, because obviously, it's no more just verification doesn't mean simply RTL verification. This means all kind of different tools. But how do you compile now the coverage data? Because in the end, you want to have the coverage data across all your tools, across all hierarchies and levels. Like mentioned here, modeling, RTL, gate level, FPGA, emulator, and there are some challenges. There are some compatibility issues. Not all tools are working together. They are partly speaking a different language. Not everything will be collected everywhere. Then, for sure, we also have now it's also reaching out to our EDA colleagues here in the audience, compatibility issues between suppliers. It's a great experience when you're getting VIPs, VIPs, verification IP, and tools from different suppliers. Unfortunately, they're not working fully together. Yes, on a high level they're working, but how should I say, political incorrect, performance then sucks. It's amazing how I can for sure understand the reasoning, but it's not helping us. Very simple. Had some debate with some of my colleagues who said, hey, it's working together, but performance is really degrading big time. And I think this is also something where, as an ecosystem, we should do better. And then, for sure, I also talked about this, that in the end, we need also the verification, not only on SOC level, not only on the level of, two SOCs working together, but we need it on product level. Some challenges. And it consists, of different SOCs, software, discrete components need to work together. And what is the right abstraction level in order to achieve this full product verification? Obviously, RTL verification is not the right abstraction level. Let's talk about this later on. Then, interesting topic, because we also have here a couple of people from university here. Hard to find verification engineers with domain expertise as of today, I must admit. So on the one side, the languages, methodologies, take UVM, etc., are quite complex. Our systems are also quite complex, and typically our verification environment requires that on the one side you understand the UVM, but you also understand the system, you understand the data which is coming in order to work with them, in order to debug them. And what we're typically getting is either senior UVM experts with unfortunately no 5G experience or very little, or we're getting 5G experts but with no UVM experience. Interesting. So how are we dealing with it? Then sometimes it's still also, and this is interesting, and now I'm really just talking from a verification perspective, still, and we just had this situation recently. We took over a team outside of Finland which had worked on design beforehand, and we wanted to move them to verification. And there was a lot of resistance because verification is still not considered as creative. It's design, it's a real work. Verification is just, work for someone, maybe for some outsourcing. But I think this is complete misconception. Because everybody, I think, knows as of today that in a classical SOC, 50% of the work in the range is in verification. I think sometimes you can argue whether it's 50% and how this distributes into modeling, into all different levels of verification, but the big part of the design, big part of the SOC development is verification, but it's still considered as something which is not so nice to do. And I think we have to change this. And together with this, and this is now where I was even, where we are still getting more concerned, and this is now really a question to university. Graduates straight from university, typically, they're coming out of this, when they have done something, they have done a bit of SOC, design and verification, but nothing specific. And I just went through some pages of major universities, and I found a lot of research work, which was about design, about architecture, about deep level implementation of SOC circuits. This is what I also did years ago. I found something about, analog. I hardly found anything about verification. Again, there seems to be a big disconnect. And the question is, how can we change it? How can we also get, in principle, I would say at least 30% of the research work at the university should look into this, because this is one of our biggest challenges. And again, maybe I missed one university in the world which is really doing a lot of stuff, but all the universities I was looking at, I hardly found any paper. I found a little bit of indication that they're doing a bit of it, but no real focus. So, this is, as said, this is not in line with our current experience as of today. Okay, let's make the time looks good. So, approaches on complexity. This was our first challenge, and for sure, usual stuff is, but just, to lay it out again, I think we basically have to break down the verification of the SOC into all different levels, and, our typical hierarchy is we are having the IP subsystem, which is, several IPs clustered with some more standard interface. We have the top level and we have the product level. We simulate on the right level to reach your coverage. So basically, for sure, the classical goal is to reach 100% coverage on IP level, and then basically do everything based on it. On our side, a bit of challenge is it's a little bit different than a classical SOC in, let's take automotive or some kind of microcontroller design where you have a lot of standard interfaces. In our side, we always have these data paths, which is non-standard, which basically have to be considered in our verification environment and test bench setup. For sure, one important point is also, which is getting more and more important even on the verification side, to have a hardware debug architecture already in the design, partly for sure to ease your verification, but also in order for preparation of post-silicon work. And for sure, we have to ensure that basically every verification work which is done on a lower level can be reused on the next level. So test bench elements, but even verification methodology, test cases ideally can be pushed to the higher level. For sure, not always all of them, because you don't want to redo them, but you also don't want to restart from scratch. And we have to use different methodologies and tools. I mentioned this. It's no more just about RTL verification. I think that's pretty clear. On our side, it's really a combination of all different tools. It's MATLAB, it's C-model based, it's formal verification. As of today, mainly connectivity. This is probably something where we have to improve further. RTL, FPGA on IP level, emulation on subsystem and top level, system modeling. And you have to combine all of them in the right way. We have to limit gate level simulation to a bare minimum. It's basically to try to check some of these topics like X-prop or meter stability already in RTL, in order again to really limit the gate level simulation. And we need to compile the feature coverage across all levels and all tools. And there are always some compatibility issues, like taking line coverage from different tools, but this is maybe again on the next slide. Then, what is our approaches on late inputs, spec software standards? So in principle, it's a challenge. Because when you're getting input too late, you definitely have a challenge. The only thing you can do is to accelerate a little bit your engineering task, system engineering task, which we are now starting to do with model-based system engineering, classical approach of, this virtualization platform. We are doing classical shift-left initiatives, enable early software development, which for sure still requires that you really have software developments that developers also early available. I remember at my time at Intel, we had a challenge. We did a virtual platform 2 years ahead of the product, and we were then waiting 18 months for the software developers to show up. So, which was then not really a big software shift-left success. And we're still having some similar challenges. And also understandable, but this is for sure something which needs to be considered. And then for sure, from a design perspective, we need to add more programmability in our designs in general, because again, you have to react to all the changes which will come up later. Then, next one, randomization versus use cases. As I said already before, and we need randomization basically on each level, at least on IP, subsystem and top level, to reach full coverage, especially when it's about feature and line coverage and this toggle and branch coverage. And we have also to continue random verification even after RTL freeze. So even on IP level nowadays, we really will run until the tape out our IP verification, at least for some IPs, because we had some interesting experience there in the past. We also need more focus on use-based verification the more you're getting to the top level. You have to start with some system level use cases already on IP level, you need to prepare them, but then you probably need more of them on the top level again in order to prepare the system bring up in the end. This is all about it. Then in the end, we have to, this is now coming back again to this rainy weather use cases, we have to generate scenarios, test vectors that minimize real field values. not idle scenarios. How do we even react to errors? How do we react really to stress the system? This is typically not something what you can try to do it out of randomization, but you have to think differently about this. Then, coverage. Okay, so on the one side it's a feature coverage. Feature coverage probably a bit easier because there you can use some kind of, outside of EDA tools, you need some kind of unified test plan, which is in a different location, in a different tool, and you have interface from your verification tool to this external tool, and you can collect all the feature coverage data. So that seems to be doable. I think we are working on this. It's not everything fully perfect, but where I really have a problem, and this is again now coming to the compatibility issues, code coverage. Even code coverage from different HDL simulators. It's an interesting challenge because there's basically very little compatibility, so nothing you can really compile. So, I don't know. This is basically also coming to the compatibility issues between the tool suppliers. So in general, what I just already mentioned beforehand. So how are we dealing with this kind of challenge? On the one side, it's really from my side, really this kind of ask, so how can EDA suppliers help us? What I said, like, for example, specific VIPs are really just working only with one specific tool. They're not working great with another tool. Obvious. So we have seen this, and, performance differences were immense. So what are the potential approaches? Yeah. Building our own in-house tools for each and everything, doing some EDA work, or going for one supplier option, basically kick out all the other suppliers. This is a little bit the option which are on the table right now, or is there something else? This is really something, this is also a question to each and everybody in the audience. This is the challenges we are having today. Then, verification at product level. This is what I mentioned before. And so how do we verify our product? And I think right now we're doing basically several approaches. On the one side, we are having high-level modeling of several SOCs together with software, which can be a high-level abstraction level software simulator, no cycle accuracy, but at least you are able to simulate a high-level system plus software together, and we are putting them together. It for sure just needs in-time availability of the models and of the software. But this is at least part of the approaches we are having today. So which basically means you're having the complete system running together, but for sure with a high abstraction level. So not everything which is real-time will be taken care of, and you some points out. Other point is what we are also doing. We are basically, when we have our SOCs in emulation, we are trying to emulate them with some Python-based models of this SOCs around them, which is again a modeling, but it's always some kind of modeling. So at least the advantage is with this approach, you have the good coverage of the specific SOC, but it's highly dependent on the accuracy of the models you're using in your Python environment. And then in the end, for sure, the classical approach, but this is then more a post-silicon approach, evaluation boards, or evaluation/product boards, basically really simulating them together. And as of today, we're doing all of them together. It's probably, the only chance we're having today. And up to now, seems to be at least a reasonable approach. Good. Challenges with verification environment, and this is now a little bit, because as I said, our requirements are to simulate our regression run in 1 week. And as of today, we're classically still using an LSF-based verification environment. We have there some challenges, but because sometimes it's also about how to really optimize the usage. So what we started to do is basically using AI/ML in order to set up the parameter configuration for the LFS environment, basically learning from past runs and come up with an optimized setting for our LSF environment. So, and this really showed some good speed ups there. On the other side, we are also now going into some kind of more cloud-based, DevOps-based approach using cloud and Kubernetes for our verification runs. It's at least an approach for IP and subsystem level right now. It shows a good speed up, but especially when you're comparing basically very similar compute power on LSF and Kubernetes, it's interesting. That it also shows that LSF as of today is a bit outdated. It's a good technology, but just a bit older. But it would be also great to work there very closely with our EDA suppliers to get optimized regression setups. On both, for example, on the cloud-based side, it really took some time to get some of the tools really up and running with Kubernetes. On the other side, also sometimes I would have wished that our suppliers coming to us and telling us really, okay, this is our best understanding how to use this kind of infrastructure in order to come to optimize regression runs. Because in the end, it's not just about, running one verification test case as speedy as possible. In the end, in our case, it's about running 5,000 use cases on a server farm as fast as possible. And this is something where, in the end, we as a, project team are then supposed to talk to EDA supplier, IT supplier, external IT supplier, and trying to redo this work again and again instead of having there some kind of good solution. This is maybe something which, I would also like to discuss in the next days. Then, verification resources. It's a topic I already mentioned beforehand. So on the one side, what we are doing right now internally, we are doing this kind of internal promotion of verification to our Nokia SOC R&D community, but this is for sure limited reach there. On the other side, we are also trying to have a better verification framework, which basically allows even people with less verification experience to easily ramp up into verification. I think another point is where sometimes also you need to be careful, because sometimes there's this kind of, especially from my operations people, there's coming these requests, hey, we should have multiple skilled people. We should have people strong in verification, design, and modeling. Unfortunately, as of today, it's a bit of challenge, because either you are a very specialist in one domain, or you're more generalist, but then you have some other drawbacks. And when you need a very strong verification engineer, the best is to pick up a very strong verification engineer. However, I think what we have to do, and this is, when I started in the semiconductor industry, verification and design was not separately. It was anyhow the same language. There were no specific tools, and every designer was doing verification, synthesis, even physical design all together. Nowadays, and this is a bit of a challenge sometimes, and it's for sure partly understandable, that more and more people are really going into this kind of domain, and sometimes, designers are just doing design, handing over the design to verification and synthesis, and just leave me alone. And this is for sure also not the most efficient approach. We need to have this more kind of working seamlessly together, like the designer has to do some verification, the verification guy has to understand the design in order to also find some of the bugs. So this is a little bit what we are also trying to push, and which also enables us then in the end a little bit more to deal with these kind of verification resources shortages. We are also looking into high-level synthesis. It's where high-level synthesis for sure, there has been sometimes this kind of comments, high-level synthesis, you're just writing a C code and, magically some kind of designer coming out of this. High-level synthesis means you're just describing your design in C but it's not the standard C. You still have to describe it like a designer. But it makes some of the approaches easier. It also makes it easier to switch from design and verification. So this is definitely some of the areas we think about it. And then for sure, discuss with universities about verification. We started collaboration with Finnish universities, but we definitely need to push them to shift also more into verification. So I think we are even having some discussion about really, helping them more directly. From my perspective, this will be under the strict guidance that we have to do more about verification. Because I don't want to have then another professor whose research is based on some specific design topics which are not helping me. Okay, and for sure we want to also have more PhD in these domains, who really have this kind of, thinking about how creative can it be in order to find the right bugs as fast as possible and to come up with a design which has basically as little bugs and highest key coverage as possible. Okay, with this I'm already roughly at the end of the presentation. So what did I present? So a little bit about, so what are the SOCs for 5G infrastructure products? What are the challenges in verifying them? Presented some approaches on our side to tackle them, to tackle the challenges. And in general, I think it's just worth to mention verification in our world as of today is a combination of a lot of different technologies, and we must combine them efficiently and seamlessly. This is basically, from a verification perspective, the biggest challenges we're having today. And ask to the ecosystem, just a summary, what I already mentioned beforehand. EDA, really to help on the compatibility issues and the verification environment. So there is really more help needed. And is there a need? And this is again, I was phrasing this a little bit more carefully. I strongly believe there is a need to get universities more focused on verification as one of the biggest challenges in our design cycle as of today. So that's the end of my presentation.
So thank you a lot, Axel, for this excellent keynote. And of course, being in Munich, first of all, you get your gingerbread. Just not so bad. Thank you. From the steering board, for this great presentation, and from the board, I cannot better have wished to give, this great start into the conference, because Axel put all the different topics we have for the next 2 days, and I hope we can also find some of the answers, and especially your call, to get the verification domain expert with looking ahead on other domains. I think that is a super important call, and yes, I hope we can help you.
I hope so too, yeah.
Okay. And now we have some time for some questions, in terms of the audience. If you have Axel put so many challenges and also some solutions, so there's one question. Do we have a mic? If not, I'm...
Have you considered using snapshots for improving the efficiency of your regressions and the turnover time for development?
Snapshots means basically start off from a past verification in order, or
to begin a simulation from time not zero.
Okay, so we are doing this with some, models where, especially when you're basically running large software on it, then it might be an option. Like, this is something what I already did, a couple of years ago. Basically, when you're talking about booting up a system, you will not run all the boot cycles again and again. This is definitely a snapshot. In our classical RTL design as of today, we are not having this in place.
There are ways to use snapshots in a way that you can recompile in the middle of an RTL simulation. that is something I can talk to you about later, maybe.
I would be interested to hear this. It's, in principle, this kind of snapshot idea makes some sense. The challenge is, okay, how does it fit on our side with having these kind of data paths coming through? And when you're basically changing something, is then still the snapshot valid? Because, the case I mentioned beforehand, when you're talking about the boot up system, then in principle, it's still the same boot code, there's no changes, the environment didn't change, so the snapshot is always valid, right?
Yeah, so there are solutions to that.
Okay.
Okay.
I think we would be interested in this.
Okay.
Definitely, yeah.
Can I write to you an email or?
Yeah, sure.
Okay.
Yeah.
Thank you.
Thank you.
Thanks for the question. Oh, the next one is just here, that's easy.
Hi, just want to ask you, do you really do power estimates at the beginning? In IP level? So.
Yes.
Okay, but you haven't shown that, so I was kind of having that question in my mind.
Yeah, no. No, that's for sure. I think, we started with this already because in the end you need to get into the power envelope. You can for sure always argue how accurate this is, but I think our success rate they've been pretty good, especially in the last design. Our power estimation was in a good range compared to real silicon values.
Hi, you talked about hardware-software co-simulations, and with the device size increasing, I think the software size also increased a lot.
Yes.
So how are you handling the lag between the software development and the hardware at your end, and how are you dealing with that?
That's so in principle. So what can you do? You can so what we did partly, and this is not covered here because part of the design cycle, we partly developing for sure more own internal software. At least we are doing our own lower level software. So this is already helping a bit. But in the end, you will be still dependent at some point in time, especially for some complicated use cases, you will be dependent on real software. So in the end, we must get software earlier. So we are really starting to push there much stronger to our internal software partners to really get the software in place. Because otherwise, the other choice would be that the SOC team is starting their own software product development or reference software development, which is an approach, and we have seen this in different companies. I've seen this in the past. But this is then also really about huge investment. Because, we just had a situation just recently in the SOC, we had even a silicon out, chip was out. Unfortunately, software didn't have enough time to work on this. They come back to us and found this is not as expected. We have a performance issue, and we could only find it even when we had all the requirements, beforehand. It was only visible in software. So, point is, we need the software as early as possible.
You did mention you continue verification after RTL freeze, and I'm assuming that is still the intention here is to find bugs.
Yes.
Some bugs maybe will be easyable, but what do you do if you find critical bugs? I'm assuming you still have schedules, timelines, and all that stuff.
It's a critical bug is a critical bug, right? Or a critical showstopper is a showstopper, and then otherwise you can still decide is there a workaround possible or not. But for sure, this is sometimes the challenges we are having there right now, because we are talking then about a product which needs to be out in the market for 10 years. So sometimes it might be then also worthwhile to even delay it for some time, because otherwise right now then you have to work with a compromise for the next 10, 15 years. But it's always, that's a tough decision, right? You're getting some kind of bug finding very late. So then we're typically having a big review meetings, some escalations in the company about what are we doing now about it.
Thanks for the presentation. A question more on the analog RF side. You showed a lot of material and methodologies in the UVM, SoC. But in the end, you are making a base station chip, and
yes.
You have to deal with antennas, MIMO, RF paths, which makes the simulation or modeling even more complex. Can you say a bit how this analog RF is part of your verification flow methodology or
do you want to talk about it? No, not so much about it. So I think first of all, I think the important part is that Nokia decided some years ago to to continue to develop really their own analog RF. So what we are basically typically having is models of the power amplifier in our environment. This for sure already describes the challenge. Because the models of the power amplifier are just models. They're not always accurate enough. So in the end, it's also then about, finding then the right approach. I did not cover this here at all, you're right. To find a way on the other one side using the model, pre-silicon, but then also having the right power amplifier and other components in our evaluation boards. And there again comes a challenge, because the typical challenge we're having is that some of the components which then in the end will be used by our end customers might differ from the components we used beforehand. And then we are typically finding some challenges. We are trying to overcome this by really also for sure giving some limitations for the analog components. But challenges in our world is sometimes that you can say only use component A, the customer will still use component C. And then they're coming back to us, it's not working. And we just have I just had a couple of our bugs reported from our customers, which are exactly about this. That's a classical challenge, yes.
So thanks to all your great questions. I see a couple of more. We have time for one more, because we have also coffee break and we start at 10 with the tutorials. But Axel is also, on the panel tomorrow, and we have exactly the next 2 days to discuss some of your questions, and he will be also available, after if you go one for your questions. So last question. Sorry for the last.
Question about the verification resources. How many people? How many sites? How long? The complexity of getting them running together efficiently.
Okay, I cannot answer the number of people we are having on verification for sure, but the ramp up is, it's an interesting question. There are different indications, and for sure it really depends on level of experience beforehand, level of UVM experience, level of domain experience. Biggest challenge for me is still as of today depends on IP. In some of the IPs there's always this kind of statement that it will take 6 to 9 months to be fully efficient, which I think sometimes it's a bit of exaggeration, but at least you will not expect to have people really fully up to speed in less than 3 to 6 months. And this is really, because it's a different scenario, like taking a classical SOC where you have standard interfaces, you're just taking your environment, and all you have to understand is the standard interfaces connected to it, and then you just have to learn about the IP. In our case, it's not only the IP, because you really have to understand the surrounding, data parcels. And this makes it more challenging.
All right. So thanks for all your great questions. And again, Axel, thanks for your inspiring keynote. And now have a good break. Okay.